In this computing systems lecture, we're going to look at input devices, I/O, and 3D and gaming, so a mixture of topics here. Input-output refers not just to the use of keyboards or controllers or displays, also refers to transfer of data to and from the hard disk and network communications and so on. The common feature that all I/O has is moving data from one device to or from main memory or to or from CPU. So keyboard is obviously a very standard form of input and is the most simple, perhaps the most obvious form of input for computer programs. Two key forms of input: polling and interrupts. With polling, we have a system whereby the CPU regularly checks all of the input devices to see if any of them have some data that the CPU needs to process. With an interrupt, the CPU goes about its normal business running a program, and when a device sends an interrupt signal to the CPU has to halt its normal processing and deal with the input. So polling is kind of like this. We have some program that's being run in the CPU, and it runs for some period of time, and then it pauses while the CPU checks to say, is there any input for me? If so, deal with it, and then it will carry on continuing its previous operation. So even when there is no input, the program is going to keep pausing just to check whether or not there is input for it. With interrupts, it's a different system altogether, and this is more of a slightly hardware view. And what happens is the program's running, doing its thing, but a special interrupt request line connects to the CPU from the different input peripherals, and any time a signal is received there, the CPU can then say, oh wait a minute, there is some input for me to deal with, and it can use the address bus and data buses to get access to different devices to get the input that has arrived. And how this actually behaves is more like this. So our current program is shown in blue, and it just goes around doing its normal thing until an interrupt signal is received by the CPU, which causes the CPU or the operating system to start an interrupt handler. And this is a special program that saves what the program was currently doing, saves what the CPU was currently doing, saves all the current register values and saves all the data, so it can then deal with and respond to the interrupt signal, does that, and then it restores the current program, goes back to where it was and carries on from before. On the x86 systems, and so standard Windows PCs, there's a range of different interrupt requests, and this is obviously quite a dated system, and you can see that how dated this is in a way, and it's a very legacy bound system because many of the interrupt requests deal with particular devices that aren't often used nowadays. So IRQ5 and 7 were originally to do with line printers. Nowadays they may be used for sound cards or even other devices that can be mapped to other things. IRQ6 was a floppy disk controller, and most computers nowadays don't actually bother with floppy disks. So some of these are still used for their original purpose. Other IRQ interrupts may be mapped for other reasons. So some of them are specific to mice or to coprocessors or to other devices such as hard drives and CD drives. So the operating systems have actually added extra layers of flexibility on top of these original interrupt requests to make them more general or to make them apply more to modern devices. It's worth noting there is a comparison or a similarity between different styles of programming for event handling. So if you're writing a game, for example, then you might want to regularly check whether there is any keyboard or controller input, and games often do some form of polling, and so they check for input at fixed time intervals. Could be considered wasteful to do all these checks, but the checks don't take very long. But by doing them at fixed time intervals, it means that the game performance can be predictable. You know how long the game loop is going to take because you're checking for input at a set interval, and it's fairly predictable and reliable. If you're programming for Windows and you've got, for example, a window with lots and lots and lots of buttons, you don't want to poll all of the buttons and possible inputs on a window. Instead, you will wait for the user to click on something. And Windows programming is typically event-driven. The program may have some of its own processing to do, but it might spend a lot of time just waiting for the user to click on something. And so that's an event-driven programming style, and is in a way similar to how operating systems and computer hardware deals with the interrupts. So there's just some similarities there. They are different systems, but they're a little bit similar in principle to polling and interrupts for hardware I/O. An issue that's very important for getting good speed for I/O is direct memory access. With direct memory access, devices can manage the data transfers without the CPU having to be in charge of moving data. So, for example, to move data between main memory and a disk drive, if the CPU is in charge, the CPU has to start the process, manage the process and end the process, and it keeps the CPU busy doing all this data transfer. With direct memory access, the CPU can perhaps start the transfer or ask for the transfer to happen, but it doesn't have to be processing it. It can do its own thing. So a separate controller called the DMA controller and some additional circuitry can handle this instead. While a direct memory access transfer is occurring, passing data, as I say, between main memory and hard disk, the CPU cannot use the data bus, but it can do its own local processing. Key DMA modes are burst mode, which with burst mode, the direct memory access controller will take control of the bus until the transfer is complete. So it's going to say, I'm passing data just now, so nothing else can use the system bus because I'm using it to pass data. There's another format called cycle stealing, sometimes called transparent DMA, and with cycle stealing, the DMA use of the bus is interleaved with the CPU use of the bus, so they each alternate, so they each have sort of one bus cycle for passing a bit of data for the DMA transfer, and then the CPU has access to the bus for one cycle. Now, if the CPU has got a large local cache memory and is operating on data that it stores locally on its cache and doesn't need the bus, then cycle stealing can be wasteful because the CPU might not actually be needing to use the bus very much. But there may be situations where it is actually more efficient, because with burst mode, while there's this data transfer going on between memory and some other device, the CPU can't access memory or do anything else that requires bus access, and that could stall the CPU. That was a very brief mention of direct memory access and that sort of memory I/O element. There's much more to read, and I recommend reading up a little bit more on that on Wikipedia, and just to fill in more on that. But we're moving on quickly to have a look at some different input-output devices. So the mechanical mouse isn't so often seen nowadays. We'd use some kind of discs that would turn as you moved the mouse over. So moving the mouse would rotate this ball in the middle, which would rotate the discs, and the discs would then have a sort of light encoding, so there would be some sort of discs with holes in them, and a light sensor would pick up the rotations of the discs, and we'd be able to use the speed of those to work out the X and Y speed or velocity of the mouse itself. But most mice these days are optical mice, and these use lasers, and it's the reflection of the laser from the surface and how it reflects is able to be used by a sensor to detect how the mouse is moving across the surface. Early optical mice needed to use special mouse mats with black and silver patterns etched on them so they could tell how the mouse was being moved over the surface. Modern optical mice don't need any special surface. They can be used on pretty much anything. You may get different effects depending on how the light reflects on particular rough or smooth surfaces. Trackpads are very common on laptops especially, and some trackpads like the modern Mac trackpads also offer multi-touch, so as well as just being able to use it like a mouse pointer, you're able to do gestures like pinch your fingers together to zoom in to zoom out, or put your fingers together and then spread them apart to do a sort of zoom out gesture to pinch in on an image so you can enlarge or reduce something, or to use different swipes and other gestures that can be detected to trigger different effects. Gamepads will be very familiar to many people, I would imagine. Lots and lots of different buttons, so there are 4 shoulder buttons where we can see L and R perhaps at the top of this controller. There's actually 4 buttons just out of sight there, 4 buttons in the left and right. We've got these 2 sort of analog sticks, and these are little joysticks here and here that we can move in multiple directions, and they also have buttons so we can actually depress these as an extra button. And on top of this, the Sony controllers have 6-axis control, which means they have tilt sensors as well, so they can detect as you tilt the whole controller from side to side or up and down. And these controllers also actually have a feedback mechanism. They have some kind of rumble pack or inertial device so that they can actually shake and give you a sensation of movement through the controller. And that means that the controller is mainly an input device, but also actually provides some form of output to the user as well. The Nintendo Wii will also be familiar to many people, and the Wiimote is primarily a motion sensor, and so as you wave it around, it can detect roughly where you're pointing it at, but also detects the motion of the Wiimote itself. It's paired with something that's called a sensor bar, which plugs into the Nintendo Wii itself, which is slightly misleading because the sensor bar is actually an IR transmitter, and it's actually detected by a sensor in the Wiimote itself, which allows the Wiimote to sort of work out its orientation and position relative to your user's television. And then there's a number of buttons and there's a trigger underneath as well, so there's a number of other input devices as part of that. And that really opened up a wide range of gaming for a much broader, more mainstream audience than before, because suddenly for a lot of games you were able to control the games by waving your hands around and doing things in a much more natural system, and it wasn't quite as hardcore or focused on a particular game audience as the previous gamepad is. This was much more of a sort of family thing, a much simpler controller, very few buttons, very easy to use. And then this has been extended, so with other motion input devices, so the PlayStation now has the PlayStation Move, and the Xbox has something called the Kinect. And there's a Kinect sensor here, and this actually has multiple sensors. It has an RGB camera in the middle, an infrared laser projector, and a sensor for range finding. And what this means is it's able to actually build up a 3D depth image of what's in front of it, so it can actually, with much better accuracy than just with a normal camera, it can actually pick out and identify people standing in front of it, and people moving in front of it as well are picked out much more easily than with a simple camera input device. It also has a microphone array that allows it to do speech recognition and also work out speech localization, where sounds are coming from. And so these Kinects and Wiis and gamepads are very widely used input devices nowadays. And Kinect broke records as being one of the top selling or fastest selling high-tech gadgets of all time in the UK, so it had a very good success rate in terms of sales. And if we look at a modern mobile phone such as HTC Desire, which is an Android phone, it's got a huge range of different inputs and outputs. So we've got this screen here, which is a touch screen, so it detects our actions on the screen and detects how we use it with using the screen itself as an input device. So it's obviously an output device, it's also input, and it's multi-touch. There's also a compass, an orientation sensor, so it can sense tilt as we tilt the device from side to side or up and down. GPS, so it can work out where its position is in the world. So there's a huge range of different input devices there, plus of course a few buttons as well around the side. And some Android phones also have full keyboards, so you can have full text keyboards as well as additional input. recently Google announced a new program which is going to be allowing peripherals to connect to Android devices via USB, and that's going to mean that things like gamepads and a whole range of other input devices will be able to be used with Android phones and pads. That was a very quick through I/O, both devices and how computers deal with and work with I/O. Now we're going to have an equally quick and rapid run through of computer graphics. Most computers up until the late 1970s were limited to text output. Early graphics displays, when they existed, could be either vector or raster based. Vector displays would control the beam of light in a cathode ray tube to draw lines, and they could give very fine lines, tended to be limited to just one colour though. Weren't very good for multiple colour displays. Also not so good for text, but very good for fine drawing of images or shapes, outlines of shapes particularly. Raster displays, which is what everyone really uses nowadays, split the screen into rows and columns of pixels or picture elements, and we have some kind of memory screen buffer that holds all of the colour or grey values or black and white values for all of the pixels. Here's an early form of computer art, and this was ASCII art. With limited graphical output, a lot of computers were really limited to using the character set, different characters and letters, to actually be able to produce art. This is an image of Coates Memorial Church in Paisley, just opposite the university, produced using an ASCII art generator at glassgiant.com. And you can try this out for yourself and take any images of your own, post them through and see how they come out as ASCII art. Now if you look in this, obviously you can see that the whole image is made up of different ASCII symbols. And it's maybe not as completely recognisable, but you can see roughly that it's a church, and especially when you know what it is, it makes it even clearer. Now here is a 3D model of the same church, but this time we've got it in a 3D virtual environment. And we've got graphics and we've got textures here, so it's a bit more recognisable. Perhaps not as the particular building it is, but certainly it's more recognisable as a kind of church and a kind of in a semi-realistic setting. If we were to look at that same image as a wireframe image, we can start to appreciate some of the depth of detail and the amount of detail that has gone into producing that one computer image. So what we've done is we've switched off the surfaces of each shape that's being drawn, and what we're seeing are the corners of every shape, and we're seeing all of the triangles that have been generated to produce that graphics display. In class, I remember someone asked, why do computer graphics usually use triangles in 3D output? There are actually a few reasons. One is that triangles, shapes that are limited to 3 corners, are guaranteed to be flat, so all the points are in one plane, and that has some important advantages, because if you're trying to draw a flat surface, but actually the 4 corners, for example if you're using a square, if the 4 corners happen to not be exactly flat, then you can get some undesirable effects. And also you can't have any concave shapes, and again it's a way in which you can remove undesirable accidental effects, and you're guaranteed to have things render properly generally if you're using triangles for the shapes to render with. So you can see this whole image is made up of huge numbers of triangles. So each side, each part of the building is made up of lots and lots of triangles. Each vertex might have a different colour. We have lots of surfaces to draw, and if we go back a second we can see we're also applying textures. 2D graphics are being basically applied to the 3D surfaces to make things look more realistic. So there's a lot of being processed in that one image. If we look at the tree, for example, where there are some curves, we can see there's huge amounts of data to draw that one tree. The tree trunk here has got huge numbers of vertices. And so when we're drawing in 3D, we're working with a number of things. So a vertex or a vertex is basically one point, and it's usually we're talking about a corner point of a triangle, or it could just be a point or one end of a line. So we have lots of vertices, and that one image had thousands of vertices in it. We then have lines and polys. So a line is a line, obviously. A poly is any polygon, a shape with a number of sides. And usually we work with triangles, but we can work with other shapes as well. The shapes have to be filled in. We have to apply some kind of colour. We might have to apply shading, so light and shade to surfaces, apply textures, apply the images to the surfaces, and then there are other effects that can be applied as well, things like bump mapping or normal mapping, and these kind of model the effect of rough surfaces. So you can see how the light or shade applies to, or is spread across a rough surface. And you can perhaps see the bumps and grooves on a surface. And then there's a huge, massive range of different visual effects that can be applied as well. Different light effects, different glossy or glowy effects. There's a huge range, things like fog and so on and on. It goes on and on. Graphics cards and GPUs normally have their performance measured in one of a number of ways. So sometimes you might see triangles per second. How many million triangles or polygons can be drawn in 1 second, or a fill rate is sometimes used. The performance of actually taking those triangles and filling them with colour or applying textures to them. And there is a huge and confusing range of integrated and discrete graphics cards available, and they all have different model numbers, and the model numbers all mean something a little bit different. And I recommend, if you're serious about shopping for a graphics card, go to a site like tomshardware.co.uk, where they regularly review a wide range of different graphics cards and point out which ones are best models for particular budgets and price ranges. Because you will find that there will be graphics cards with what appear to be similar stats or similar abilities, perhaps the same amount of RAM. So you might have two graphics cards that both have 1 GB of RAM. Which one is better? How can you tell? And it can be quite confusing if you really are shopping for a performance graphics card. So do have a look at something like Tom's Hardware. They have monthly roundups, and even having a wee look at those will give you some idea of the huge range there is in graphics cards, and the huge range there is in graphics performance from different graphics cards. When it comes to light and shade, to illustrate the importance of light and shade, without this sort of shading, a surface will appear flat. So we have a circle here where across the surface it's the same sort of shade of blue, or same shade of lilac in this case, and it looks quite flat. Here we have a dark blue circle, and we can see we have a highlight here, and we have more shadow on this side. And this is similarly shaded, but here we actually have one colour more spread out over an area, a part of the surface. So it's a different shading model has been used to generate this. But we can still see the shape. So we can only really see the shape of the sphere when we have light and shade applied to it. Without light and shade, the shape just goes flat. Now, it's important to note that the description in the book, How Computers Work, is misleading. In graphics programming, shaders and shader programming is used to refer to special programs that can be loaded onto and run on the graphics processor unit. And also the terms refer to the graphics processor hardware that runs these shader programs. In contrast, shading calculations are performed to achieve realistic lighting effects, and that's with or without shaders. So there's a big distinction in graphics programming between shaders and shading. Shading is doing lighting calculations. Shaders are the programmable hardware on graphics processors and the programs that you use with those. And that's a relatively recent innovation. Older GPUs had fixed programs, so all graphics data had the same set of operations carried out. You could programmatically opt to have particular steps applied or not applied, but you couldn't run your own programs on the graphics processor unit. So your CPU might pass in data to the GPU and tell it what to do, but it couldn't give the graphics processor unit a new program to run on it. Modern graphics processor units contain multiple shaders, multiple shader units, and programmers can write special programs to run on the graphics chips themselves to modify and customize the graphical operations to be carried out. These are actually very flexible and can allow the shaders and GPUs to be used for scientific data processing. Now, what a graphics card does is it's specially developed to process huge thousands, hundreds and thousands of bits of data at the same time, doing the same thing to each bit of data. Whereas CPUs are generally optimized to do one instruction that could be anything at all on one piece of data, then do another instruction on another one piece of data. GPUs are much more optimized towards performing repetitive calculations on large batches of data, and that's very useful for generating 3D graphics images, and it's also useful for scientific data processing. And so modern GPUs are sometimes used to build even supercomputers largely built out of GPUs. They've been very heavily optimized for geometric and mathematical operations, and so that's another application for them. Here's just one example of an image that's been created using a programmable shader. This is I think it's an open source 3D model, and it's a student at UWS created a shader that renders this model and applies a particular method called ambient occlusion. And ambient occlusion is basically a method for creating better shadows within a model. So the normal lighting would create patterns of light or dark based on the angle between the viewer and the light and the surface of the model, but that wouldn't give particularly defined shadows. What this does to give more defined shadows is uses this rather complicated technique, does lots of random sampling and tries to identify the bits of the model that are within sort of folds, and so that's almost like the inside of the elbow or in the folds of the robes here. And that gives you some very subtle and some very nice lighting effects and shadow effects across the model. Lots more for further reading in Wikipedia, because we've actually run through a whole range of different material in this quick lecture. Interrupts, direct memory access, different input devices such as mouse or trackpad and touchscreen, Kinect and so on, computer graphics, shading and shaders. And Principles of Computer Hardware Chapter 10 is on I/O, and that will actually go into a lot more depth on things like interrupts and direct memory access. And image credits for this week as usual. And that's a wrap.